Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on the inclusion-exclusion principle, in which I will discuss about derangements. We have three objects: A1, A2 and A3. The original place of A1 is place 1. Original place of A2 is place 2. And original place of A3 is place 3. We may rearrange these three objects, means we may mutually interchange their places. The name of this interchanging is permutation. So we get following permutation. Here A1, A3, A2. Here A2, A1, A3, A2, A3, A1, A3, A1, A2, A3, A2, A1. Here we get 6 permutations. In the first permutation, here we see that A1 is its original place, place 1, A2 is in its original place, place 2, A3 is its original place, place 3. In second permutation, here A1 is its original place. In third permutation, here A3 is its original place. In fourth permutation, we see that no object is in the original place. So we take this. Here we see that no object is its original place. So we take this. Here we see that A2 is its original place. So we do not consider this. We do not consider all those permutations in which at least one object is its original place. So we cancel this. Here also we cancel this. A1 is its original place. Here A3 is its original place. Here A2 is its original place. So we cancel this. We get only 2 permutations in which no object is in its original place. These 2 permutations are called derangement. So we get derangement A2, A3, A1, A3, A1, A2. 2 derangements. Here we see that derangement is also permutation in which no object is its original position or place. Now we define the derangement. A derangement of a sequence A1, A2, comma, An of n objects is an arrangement in which no object Ai is in its original position. That is, no object Ai is still in the ith position. Now we prove a theorem. Theorem is the number of derangements of n objects is equal to Dn equal to factorial n under bracket 1 minus 1 by factorial 1 plus 1 by factorial 2 minus 1 by factorial 3 plus plus minus 1 to the power n 1 by factorial n bracket closed. Now we prove this. Let A be a set containing n objects a1, a2, an. Let S be the collection of all permutations of n objects a1, a2, an. Therefore, number of elements of S means number of permutations of n objects will be factorial n. Let Si be the collection of all those permutations in which ith object remain in its original position. Means ith object in its original position, it will not interchange with other objects. So remaining objects are n minus 1 and they will interchange their places. Therefore, number of elements in Si means number of permutations in this case will be factorial n minus 1. Because keeping ith object fixed in its original position, we interchange the places of remaining n minus 1 objects in factorial n minus 1 ways. Similarly, Sj means collection of all permutations in which jth objects remains in its original position and number of elements in it equal to factorial n minus 1. Let n1 be the sum of all these type of permutations, means first object remain in the first position and we take the permutation of other n minus 1 objects, then second object remain in the second position, we interchange remaining n minus 1 objects. So if we add all these permutations, we get nc1 factorial n minus 1. nc1 means n. By keeping one object in its original position, we get number of permutations factorial n minus 1. Similarly, by keeping n objects in its original positions one by one, we get n into factorial n minus 1. This is n1. Let this is number 1. If ith and jth object are kept in their original position, then number of permutations of remaining n minus 2 objects equal to factorial n minus 2. We may write this as Si intersect Sj, number of elements of Si intersect Sj equal to factorial n minus 2. Let we take sum of all possible permutations, that will be S sigma Si intersect Sj. This is equal to n2 let, and this will be nc2. Means we take two sets out of n sets, and permutation for each this type factorial n minus 2. And similarly we may take S1 intersect S2 intersect Sm sigma. This equal to Nm equal to Ncm factorial n minus m. By using inclusion-exclusion principle, the number of permutations in which at least one object remains in its original position will be n1 minus n2 plus n3 minus ... plus minus 1 to the power n minus 1 ncn, and n1 equal to nc1 factorial n minus 1 minus nc2 factorial n minus 2 plus nc3 factorial n minus 3 plus ... plus minus 1 to the power n. This ncn means 1. Let this is number 2, this is number 3, and this is number 4. Here we see that the number of permutations, there is at least one object remain in its original position. So number of derangements Dn equal to total number of permutations factorial n minus these nc1 n minus 1 factorial minus nc2 factorial n minus 2 plus nc3 factorial n minus 3 plus ... plus this is minus 1 minus 1 to the power n minus 1 multiply 1. This is equal to factorial n minus factorial n factorial 1 factorial n minus 1 multiply factorial n minus 1 minus factorial n factorial 2 factorial n minus 2 multiply factorial n minus 2 plus factorial n factorial 3 factorial n minus 3 multiply factorial n minus 3 plus dot 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 plus minus 1 to the power n minus 1. This equal to factorial n we take common. Here remains 1 minus. Here factorial n minus 1, factorial n minus 1 cancel, and we have taken common factorial n. So remains 1 by factorial 1. Here plus, minus minus plus. We have taken common factorial n. Here factorial n minus 2, factorial n minus 2 cancel, only remains 1 by factorial 2. Similarly here 1 by factorial 3 plus dot 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 plus minus 1 to the power n. Here minus 1 and minus 1 to the power n minus 1. Minus 1 to the power n by factorial n. This is the required number of derangements. Thank you.